Okay, so guys, hitting the Wayback Machine, this is where we ended this conversation. We talked about the idea that we can study the energy that's given or taken during a reaction. Oh shoot, this is frozen, sorry. Guys, we can study the energy given or taken by a reaction by capturing up that energy in a process that we call calorimetry. Poor Lindsay had to watch the entire hour 30 screencast because, guys, if you remember when we did this, second period bled directly into third period, and we got to be clear on this. So, guys, on the unit test, which we are going to get in second quarter, and on the AP test, this is all you need to understand. So, guys, you've got to understand that this involves aqueous chemistry. It has to happen in the presence of water. But we assume that this cup is a perfect insulator, and we assume that the parts of the calorimeter do not absorb energy. Guys, on the test, they will tell you that because they will say, assume that all the energy lost or gained by the reaction is gained or lost by the water in the calorimeter. And guys, the minute that becomes the case, we just need Q MC delta T. And if we know the mass of the water, this is 4.18. If we know the temperature change of the water, we can figure out Q, and we assume that the energy, let's say, gained by the water was lost by the reaction, and then we can figure out a delta H. So one thing to point out, and then we're going to move forward. So guys, imagine that the temperature of the water went up. Is the reaction endo or exothermic? Good, right? Because system and surroundings, right? The water is the surroundings, and if the temperature of the water goes up, that means the reaction, the system is losing energy, and consequently, an increase in temperature indicates an exothermic process because energy is leaving the system into the surroundings, and we say Q lost is Q gained, and off we go. So, guys, with that said, remember then that in lab, we do this completely differently. Because in lab, we account for the energy that is gained by all the bits inside the calorimetry. And we do that by calibrating our calorimeter and figuring out heat capacity. And remember, we're going to do that by mixing hot and cold water. And then we're going to do that safety check because we know the temperature should come to the average because the masses are the same. But where will our temperature be relative to the average? Above or below? Slightly below. Where did that energy go if it's not there, if it's below? Where did the energy go? Into the calorimeter, and that's how we will figure out the heat capacity of the calorimeter.
Why do you need to add two different temperatures? Can't you just add one temperature to see how much it lost?
Well, you can't because that's a really interesting question, Michael, and the answer is no. The reason is because we're not really worried about how much energy the water loses. We're worried about the amount of energy the calorimeter gains. And the problem is that, remember, we can't directly measure energy, right? We've got to measure temperature changes to infer energy transfer. And so the idea is that there would be no way for us to know how much energy the calorimeter gained because we don't have a starting temperature. So the easiest way to do that then is because your assumption would be that all of the energy in the hot water would go into the calorimeter, and there's no, does that stop at freezing? Does it stop at absolute zero? There's no comparison. So the easiest way to know the temperature of the calorimeter is to put cold water in it and allow those to come to thermal equilibrium. And then at that point, we have a starting point from which we can then figure. So what you're going to see is that in all three of your trials, the change in temperature is going to be, the starting temperature will be the temperature of either the water or I think you put the acid in first. It'll be the acid or the water in the calorimeter. And we're going to assume the calorimeter and the water or acid are at the same temperature. And then the energy change comes from there. So that's a great question. So guys, and then also remember that we do attribute for or account for the energy that is lost eventually through the cup. And if you remember, we're going to graph time versus temperature, and we're going to put our time 0 right here, and this will be the temperature of whatever's in the calorimeter. Could be the cool water, could be the acid, and then when we add either the hot water or the base, the temperature goes up. But then we're going to continue recording temperatures, and it goes down and down and down, and then we're going to extrapolate this line, measure up from there, and that will be our final temperature, accounting for the fact that the calorimeter is bleeding energy, not just after it hits its peak temperature, but all along as those things are mixing together. So guys, that was an amazingly quick review of everything we talked about whenever we talked about this. What questions do you have? You okay? You're good? Okay. Yeah, please, Ivan.
So, you said if exothermic with the water, there's some updates?
Yes.
So it would be endothermic if the degrees in the sample would go down?
Good for you. Yeah, and if you think about it, what's happening is whatever that reaction is that's taking place is sucking in heat as the reaction is happening, so the temperature of the water would drop. Yeah, you're not going to see that in lab today. So in lab today, both of the neutralization reactions are exothermic, but when we come back next week to do the next lab where we're going to start dissolving salts in water, a significant number of them get colder, and you'll have to keep track of that. Yeah, that's a great point.
I was like, normally where this for updates,
Yeah.
this time in water.
Exactly. Yep, you got it. Guys, any other things to talk about? Okay, then let's do this. Let's now, Mila? Yes.
So if the reaction is endothermic, but the water will lose energy, but the calorimeter will also lose energy.
That's correct. Yeah, and so let's talk about that really quick. So, yeah, so if whatever that process is endothermic, on the AP test, they'll simply say that assume that all the energy gained by the system is lost by the water. You'll notice that on the AP equation sheet, there is not an equation for specific heat. So the only way on the AP test that they want you to be able to quantify energy exchange is by water losing energy or gaining energy. Understand that when we do the lab next week with the dissolving salts, we're going to cheat. We're just going to do it like they do in the lab to try to keep track of all. But you could figure out the heat capacity, and you could track the energy lost by the calorimeter. And also interestingly, you can keep track of the energy that's actually being sucked through the wall of the calorimeter as the process is taking place, again, by graphing it over time. But frankly, when we do this, you're going to see that when you do these calculations, the amount of energy that's lost to the calorimeter and the amount of energy that bleeds through the walls is so small that we're just going to ignore it when we do the next lab. So, yeah. Guys, are we all good? Are we groovy? Okay. So this then is where we are at. If you do it fast enough, Mila doesn't laugh because she doesn't notice. Okay. So guys, this then is where we're at. We are now going to climb down the right-hand side of our little dichotomy. It's not even a key. It's a flow chart, if you will. So guys, remember when we started this conversation, we talked about the idea that we have thermochemical equations that not only tell us reactants and products, but they also tell us the amount of energy that's involved. Remember we said that if delta H is negative, is it endo or exothermic? Exothermic, we're in the system, energy is going out. If this is positive, the reaction is endothermic because the system, the reaction energy is going in. And then guys, this is what we did over the last couple days. We talked about being able to measure delta H values. You're doing it in lab today, doing calorimetry. Now guys, what we're going to do is we're going to do this. We are going to do Hess's law. And Hess's law is a way of coming up with these delta H values that relies upon somebody already having done the calorimetry for you. And so, guys, let's just do this now. Grab your books. You're going to need them as a reference. So, guys, again, Hess's law goes like this. The idea in Hess's law is if somebody has already done the calorimetry, and if they've come up with the energy changes for processes that can add up to an overall process, well then, guys, we've got the energy change of the whole process. So you're going, wait a minute, that doesn't quite make sense. So guys, don't write this down, but let me explain to you Hess's law in a nutshell. And actually, it's kind of an interesting story. So, you guys know that the church that I attend, it's down by the freeway, because I don't know if you know that we draw people from literally point of the mountain all the way down to Santaquin. So unlike walking to your local chapel, guys, people drive a long ways in order to get to church. But it gets even worse because then you get together, especially these high school kids, like my daughter, they get together with their friends, and it just hurts. So let me explain to you what a typical Sunday looks like for my daughter. So guys, it goes like this. This is I-15. This is Linden, where my family lives. This is UVU, and this is then also our church. And then, guys, my daughter's best friend lives in Springville. Oh, you know what? Stop. I forgot another important point. So down here we have Springville. And then here we have Linden. And then, guys, here, then here we have church. And then here we have In-N-Out. Yeah. So this is what, and let's put in mileage. So Linden to church is about 10 miles, Linden to AF is about 5, and this is bordering on 15. So guys, here's then how this goes. My daughter gets up in the morning and her friend doesn't have her driver's license. So she drives all the way down to Springville to grab her friend. Actually, she wishes her day started. So she goes from Linden all the way down to Springville to get her friend. Then they drive back up to church and they do church. Then what they do is after church, they drive all the way up to In-N-Out and then they get lunch. And then after that, they end up on my couch napping for the rest of the day. So here's the question. Guys, how far does my daughter drive every Sunday? Let's do the math. So we've got 25 miles. That's 40. This would be 40, 55, so 60 miles, right? But here then is the question. By the end of the day, how far is she gone? Zero. So guys, the idea is this, and it's a familiar idea, but it's Hess's law in a nutshell. If you know the distance of all of the pieces of a process, you can add up those pieces to figure out the overall energy change of a reaction. But now we need to talk about direction. Guys, when we talk about direction in chemical reactions, what do we talk about? Endo and exothermic, right? But guys, when we talk about driving, in this case, we can say north and south. So now all of a sudden, let's say if you're traveling south, that's a positive change. And if you're traveling north, that's a negative change. And then guys, if we do the math, what we find out is that this first trip from In-N-Out, this would be a positive 25 miles. And then when she drives back up to church, that would be a negative 15 miles. Then when she drives up to In-N-Out, that would be a negative 15 miles. And then when she comes home, that's a positive 5 miles. And we find out that that adds up to 0. Get the idea? So guys, this is Hess's law. If we know the energy of each of these little changes, we can add up the energies and we could then figure out the energy of the overall change. But sign matters. For us, it's not north and south, it's endo or exothermic, but those signs matter when we do the changes. Now, the difference is this. In chemistry, very seldom do these add up to 0. So basically, for the story to hold true, she would probably have to spend the rest of the day at In-N-Out. And she'd like to do that too. But guys, the fundamental ideas are there. We need to now be comfortable with this idea. If we know the amount of energy, distance, involved in a series of changes, and if these series of changes add up to an overall event, like her day, then we can figure out the overall distance or energy of the changes by simply adding these things up. Does that make sense conceptually? Now let's do it chemically. So guys, it looks like this. We're going to do this, and we're going to do this, and we're going to do this, and we're going to get rid of this, and we're going to grab this. And guys, this is how this goes. This is where you want to start taking notes. Hess's law. So guys, rather than writing this down, let me just ask you, given what we just did, read this and tell me if it makes sense. Does that sit okay? So guys, when we read the word enthalpy change, we're talking about endo or exothermic energy in and out. We understand that if we can take like my daughter's day, and if we can break it into steps, and if we know the magnitude, the distance, and the direction, plus or minus, or in this case, endo or exothermic, guys, those things will add up to the overall change. Do you need to write down the words, or do you have the understanding? You're okay? Okay. So guys, with that said then, we need to dig into this a little more deeply so that we can sort through this and make this become something that we can use conceptually. So guys, what you're going to find is this. This you want to write down. This is the evil game that the AP authors set you up for. Guys, what you're going to see in the test, what you're going to see on the AP test is there's two different ways that we can do Hess's law. And guys, I used to teach these completely separately until I had this aha moment that turns out they're both based in the same logic. They just look different. So guys, you are going to learn both of these problem-solving processes, but we're going to link them conceptually, which makes this better. So guys, one of the things they're going to do is Hess's law by manipulation. So basically what they're doing is they're manipulating you to solve these by manipulation. I will show you what this looks like, and I will show you how to solve them. But then, guys, there's another way to approach Hess's law, and it's through computation using heats of formation. Those are words that are worth writing down because these are going to be things that you're going to be drawing on a lot. So, guys, here's how this is going to go. We're going to do one of these by manipulation. Again, it's the idea of the parts adding up to the whole. We're going to do this through manipulation. Then, guys, we're going to take a pause and we're going to explain what heats of formation are. And guys, you should know it's technically enthalpies of formation, but we use heats because we sort of use them interchangeably. So when you get to college, you'll even hear your professors call these heats of formation. Yeah, but they're technically enthalpies of formation. Do you ever have professors that actually make you tell the difference between use heat and enthalpy separately? No? Okay. We should introduce you. Please introduce yourself.
Hi, I'm Lauren. I'm a junior at BYU, so I'm just here
So 276, right?
yeah, so I'm a chemistry education major, so I'm a chemistry teacher in high school. So I'm in an exploration of teaching class, which involves observation hours.
Yeah, and it also involves you maybe getting up in front of a group of kids, right?
Essentially.
And you're always welcome to do that. Not with my AP kids, but you'd be welcome to do that if you'd like. So anyway, the bottom line is she is hot in the middle. Are you doing PChem right now?
No, actually, I don't have to. I did OChem. I just finished up.
Which is, okay, did you have a female professor?
No.
Male professor?
Yeah.
Did you hate OChem?
Yes.
Okay, good. So, I've been telling these guys OChem is horrible, but I understand there's a female professor at BYU that actually makes it understandable and therefore good. You had a male professor and you hated it as much as I did. Okay, so guys, when you get to BYU, if you get to BYU, when you take OChem, look for the woman.
I'm pretty sure you're talking about Dr. Stowers. Would be the one that teaches organic.
Could be Stowers. I just stay away from men is what it comes down to. Bottom line. Anyway, but the bottom line, guys, is she's hot in the middle of this. So if you have questions like, is freshman chemistry actually 150 people and nobody knows your name and you actually learn everything from a book in your TAs?
Yeah.
Aha! I'm not lying to you. Okay, so guys, the idea then becomes this. We're going to talk about heats of formation and then we're going to do this by computation. But what you're going to see, and most people don't teach it this way, these are actually the same. There's two ways to approach it, but conceptually they're the same, and that's how I'm going to present it to you because you guys are smart enough to get it. Okay, so guys, you ready? Manipulation first. Write down manipulation. And now, guys, this is how you're going to know you're being manipulated into doing these by manipulation. You want to write this down. It's a sample problem. The instructions will say this: calculate the enthalpy of combustion of carbon to carbon monoxide. Well, okay. That doesn't sound like fun, but okay. But then, guys, they will give you this. Skip 3 lines, and they will give you this. And please write these down. It doesn't need to be big, but I would encourage you to write these centered on your page rather than left justified like my slides. So skip down 3 lines, and they'll give you this, and they'll give you this, and you can't see either one. But guys, I would write these big enough that maybe they take up half the page, like wide, but centered. You don't need to include, you don't need to include the subscripts, the solid, liquid, gas stuff. You can skip that for now. We'll talk about it more later. How you guys doing? Maybe. Yeah. You're going to find out, Clara, that we actually will start balancing equations with halves. Oh, yeah. Like one of them we're going to look at is 15 halves. Uh-huh. That's a great question. Isn't half of O2 just O? And the answer is no. We still have, good. It's half a mole of this. So it's still O2, it's just we have half a mole of it. Exactly. That's a great question. You know what? It's fascinating. I just watched a video on this. It was an American Chemical Society video, and they're trying to make chemistry sexy. Not that we don't already know that it is, but thank you for chuckling. But they actually just did this ACS video on what happens to space junk. So there are literally tens of thousands of pieces of junk in orbit around the Earth right now. And I mean, things the size of a bolt can bring down satellites and spacecraft because they're flying at like 14,000 miles an hour. And all of a sudden they're ripping holes in things. So they were talking about what happens to space junk, right? Like, does it break down? And it turns out, you know, Elon Musk, being the lunatic egotist that he is, launched a Tesla into space. Yeah, right. And it's actually now in orbit around the sun. And to make it especially funny, he was playing Ground Control to Major Tom by David Bowie. Anyway, so the question was, what is happening to his car? And the answer is interesting. It's actually rusting. And the reason that it's rusting is because as it was in our upper atmosphere, the pressure is so low up there that diatomic oxygen doesn't exist. It's atomic oxygen at those high altitudes, and you know how reactive oxygen is, right? It's looking for other oxygens to bond to. Well, it actually tears the crap out of metal, and so the rusting processes up at those altitudes are not metal plus water plus oxygen. It's actually just metal plus monatomic oxygen, and things are breaking up. I'll send you the link. It's fascinating. Okay. All right, you guys good? So here's the deal. Guys, you have just been manipulated into doing this by manipulation. And here's why. You have been given, well, not subject, wrong word. You have been given thermochemical equations that you are going to have to manipulate. But then, guys, the question is this. Manipulate to do what? So, guys, the first thing that they're going to ask you to do is this. And you know what? Hold on. Why don't I just make mine with the same space that you have? And, I'll get rid of that bullet later. But while I'm doing that, oh shoot, that's not what I wanted. We'll just leave it there. Give myself some space as well. Each one of those is a click. Okay, so guys, the first thing that we need to do is we need to write what is called our subject reaction. So it says calculate the enthalpy of combustion of, thank you, Mila, of carbon to carbon monoxide. All right, so guys, it goes like this. Carbon, do this with me, to carbon monoxide. Is that okay? So guys, in order to do this, we need some oxygen. I want to leave myself a little more room. So to do this, we need some O2. We need some O2. Guys, as we get further into the day, let me just mention this to you. So the next lab that we're going to do, are you familiar with the phrase payback is So, guys, the next lab that we're going to do, guess what each of you are going to do? You're going to come up here to the board, and you are going to be publicly recording all of your data on my board. Mila, you're going down. Because every time you make a mistake, oh my gosh, the laughter, the scorn, the whole, it's out, and it's going to be recorded. Oh no, you're coming. You're coming. All right. You're coming. All right, so guys, this is now where things get weird. So notice the way that this is phrased. Calculate the enthalpy of one carbon becoming one carbon monoxide. But obviously, guys, we don't deal in ones, we deal in moles. So guys, what that means, and don't write this down, is this is fixed and this is fixed. Those have to be ones because of the way the question is phrased. So how then do we balance this equation? If these have got to be ones, this has got to be a half. No, it doesn't. Yeah, it does. Yeah, it does. That's got to be a half. So now, guys, this becomes the challenge. We have written our subject reaction. So now what we've got to do is we have got to make these reactions, Hess's law, add up to this. So guys, this is the way to do this. So you start with reaction number 1 and you ask yourself 2 questions. Side and amount. Side and amount. So guys, the first thing we run into is carbon. And we compare that to our subject reaction. Is the carbon on the right side? It's on the left, right? Left and left. So carbon is on the right side, and does it have the right amount? Well, we've got 1 carbon there and we've got 1 carbon there, so we're good. So guys, we're done with number 1. Then we go down to number 2, carbon monoxide. Is it the right amount? 1 and 1, but is it on the right side? So what we do is we cross it out, and down below we flip it over. So we go CO2 breaks down into CO and 1/2 O2. But now, guys, we got to keep going. Delta H is now equal to what? Positive, right? Flipping the reaction makes this positive, 283.0 kilojoules. So now, guys, what we've done, and this is the thing that's nice, they always give you just the equations that you need to manipulate to make this work. So once you have checked and manipulated all of these equations, then what you do is you bring them down. So guys, let's gather our reactants together. So we have carbon and we have oxygen in the top reaction, and then we have CO2 in the bottom reaction. So we have gathered the reactants from the 2 equations. Then we gather products. CO2 and CO and 1/2. You're going to pay, girl. 1/2 O2. Actually, honestly, the thing that I like about your chuckling is it means you're paying attention, right? All right, now guys, do you see the magic? Let's start canceling stuff out. We've got a whole mole of oxygen over here. We've got 1/2 mole of oxygen over here. Subtracting 1/2 mole of oxygen from both sides, there it's gone, and this leaves us with 1/2 mole. Then guys, here we've got a whole mole of CO2 and a whole mole of CO2. So those are gone. And guys, look at what we're now left with. A mole of carbon plus 1/2 mole of diatomic oxygen gives us a mole of CO. Do you see how the steps add up to the overall reaction? So what that then means is that this number plus this number will now add up to the energy change for the overall reaction. But guys, you got to be careful of signs. So I was gone. Oh, there it is. And I hide my stuff. You can't find my calculator. Okay, so guys, I would encourage you to do the math. Signs are going to become your downfall in these. So we've got negative 393.5 plus 283. And guys, I arrive at the number negative, actually let's put it in the proper place. Delta H is equal to negative 110.5, don't forget units, kilojoules. So guys, that is Hess's law by manipulation. They give you the equations to manipulate. You muck around with them. You make them line up. And then, guys, they add up. One other curveball. What about this? And guys, this isn't true, but let's just say, pretending. Guys, what if the equation balanced with a 2 there? How would that change things? Well, guys, when you're doing your manipulations, if this is 1 carbon and if this is 2 carbons, you would have to double everything. But if you double everything, what else do you have to double? Delta H. So that would become just short of 800. So guys, sometimes your manipulation will involve multiplication. And when that's the case, don't forget to also multiply your delta H values. You guys okay? Questions on any of that? I'll give you a second to gather your thoughts. John, you okay?
So we're just adding the
Correct. And so, sorry, there's a lot of things going through my brain. What work do you need to show? And the work that you need to show is the manipulation. If your manipulation involves multiplication, you need to put the new subscripts in front, and then you would need to show times 2 equals, and then whatever that value is. Okay? Then, once you've got the equations flipped and multiplied to the point where they will then add up, you need to show this. You need to verify that adding the reactions does in fact result in the overall reaction. And then at that point, you can just add up the enthalpies, watching charges or signs, and then you just write a statement that says the delta H for the reaction is this. Is that okay? Don't say yes if it's not. We're not in a hurry. Give it a second.
I think I'll be.
You sure?
I don't. Yeah.
Okay, so you're going to see these in homework, and if you look at them in homework and go, ugh, we can talk on Thursday. Okay? Guys, other thoughts or things you want to clarify? You're good? Okay. So now, guys, what we're going to do is this. Grab your AP equation sheets. We are now going to look at this through a completely different lens until you magically find out in about 10 minutes it's the same lens and you didn't even know it. So guys, in order to do this, we now need to change the conversation to what are called enthalpies of formation. You want to write this down. So guys, for those of you that are paying careful attention, well here, let me even do this. So enthalpies of formation, right? But then, watch this. So guys, enthalpies of formation, and then when I switch slides, watch carefully, heats of formation. We are using them interchangeably, and that will be just fine. So call them enthalpies of formation, call them heats of formation, all's good. But guys, you need to know the definition. Not because they're going to ask you on the test, what's the definition? You need to know the idea. And the definition is this. Enthalpies of formation represent the change in energy for the reaction that forms 1 mole of a compound from its elements. Guys, I would encourage you to underline the words forming 1 mole and elements. Where did you go to high school?
I'm from Wisconsin.
Wisconsin. Nice. I have good friends in Milwaukee. They like it there. Yeah, they love it there. Okay, nice. So guys, you caught up? You ready to think rather than write? Guys, I want you to think about that. Don't talk, just think. Given the definition of heats or enthalpies of formation, guys, what kind of reaction will all of these be? Given our definition, what kind of reaction will all of these be? Because what are they all going to be? They're all going to be synthesis reactions. Okay? Because what we're doing is we're taking the elemental bits and we're putting them together as the compound whole. These are all synthesis reactions. So guys, before we get into this, we need to talk about some ground rules. And they go like this. Mila? Thank you. Guys, oh shoot. Don't do that. Oh my, he's got my pen. All right. So guys, all of these are synthesis reactions, but these then are the ground rules. This is abbreviated delta H naught sub F. We'll talk. Delta, here, let me make it bigger for you. Delta H naught sub F. What's that? No. This little circle is red not. Yeah. No. It's KNOT. It's KNOT. So, guys, this is the first time. John, do you guys do the not symbol in physics? Probably not. It's not familiar. Okay. So, guys, this is a universal symbol throughout the sciences. And guys, you got to understand this. It gets really frustrating, right? I have a degree in chemistry and a minor in physics. And by my junior year, my math classes, my chemistry classes, and my physics classes were all doing the same stuff. It was awful. But, guys, this is a universal symbol in the sciences. And guys, let me just bring it up. It means at standard conditions. And this is important because energy changes in reactions change with environmental conditions. So guys, what are standard conditions? They are generally room temperature, which is 25 degrees Celsius or 298 Kelvin, and then 1 atmosphere of pressure. So when we talk about standard conditions, we have to define temperature and we have to define pressure. And if you like, because we haven't really used atmospheres, that's 760 torr or millimeters of mercury. That's the one that we've been using in lab. So 1 atmosphere of pressure, if it's helpful for you, is equal to 760 torr. But guys, here's where we are. You need to understand what the not symbol means. But here's the beautiful part. In this class, it doesn't change. We will always be doing our chemistry at standard conditions. That does change when we do gases a little bit. But guys, for all of our chemistry, we're always going to be at standard conditions. So why do they make it? Why? You'll see in the AP questions, it writes out, at a pressure of 1 atmosphere and at a temperature of 25 degrees Celsius, this reaction reaches equilibrium. It's always 25 Celsius and it's always an atmosphere of pressure. But guys, you technically have to say it it. Because if it wasn't that, equilibrium and other things would be different. So all of our chemistry will be at standard conditions, but it's technically not right if you don't mention it. You guys good on that? Okay. Then guys, this. Open up your books to page 184. Bless you. There you have it, y'all. This is definitely not exhaustive. But guys, on page 184, we have a table of heats of formation. I thought I had another book. I was trying to find you a book. I don't have a book. So guys, here we have a table of heats of formation. Guys, take a second and allow your eye to just scan over. Do you notice that it's in two separate, it should be one on top of the other. So you've got substance formula delta H, substance formula delta H, so it repeats from left to right. Guys, look it over. And let me ask you, what catches your eye? In a second, what catches your eye? So guys, what catches your eye? Yeah.
Water has a high energy.
Yes. So guys, let's talk about that. This is important. So looking at water, you'll notice that we've got water liquid and we've got water vapor. And you'll notice that they're different and that water vapor has a lower heat of formation. Guys, this is a critical idea. Don't write this down, but join me at the board. You've got to understand why. So why are those numbers different? So guys, as we look at this is the idea. So let's go water. And we're not going to identify it as a liquid or vapor, which is steam, right? We just know this. It is made from diatomic hydrogen and it is made from diatomic oxygen. But guys, the definition of this is the amount of energy lost or gained to make 1 mole of the product. So this has got to be a 1. So how do we balance this? 1/2 O2. So now guys, let's do it again just for fun. Okay, now guys, let's do this. Could you feed me the numbers, please? So delta H, not F. Give me the value for liquid water. Negative, let's just leave it at 285, and I don't have room for kilojoules. And then guys, let's go steam. Negative 241. So guys, here's the question. Why is and let's make sure we're sure, this is liquid and this is steam. So guys, why is the heat of formation for liquid water more negative? Think about it that way. Why is the heat of formation for liquid water more negative? What's the difference between the top and bottom? Let me ask it a different way. Guys, which has more energy? Steam or hot water? Steam. Let's talk about it. So guys, imagine that we're at sea level and water boils at 100 degrees. You would much rather stick your hand, you'd rather not do either, but you'd rather stick your hand into a pot of boiling water than hold it over the steam. You will get a much more severe burn holding it over the steam. Why? Steam has more energy. Why does steam have more energy? It's the same temperature. What's that? It's about moving. So guys, think about it. If we've got water, it's all about motion. I won't hit you. It's all about water. So guys, here we've got water, right? And what holds the water together? Intermolecular forces. So guys, we've got water stuck together by intermolecular forces, and then in order to turn it into steam, what do we have to do? Heat. We got to add more energy, right? Because this gets to 100 degrees, and guys, the temperature is not going up anymore. But when it boils, it's now 100 degree steam. But why does the steam have more energy? Because we have to put energy in the water to break the intermolecular forces. So the steam has more energy in it because of the phase change. Huh? So now think about this. What if we've got a bunch of steam and we want to turn it back into a liquid? What do we call that process? Condensation. Guys, in your house, where does condensation take place that you can see it? Cold windows. Because these water molecules run into those cold windows, they lose energy into the glass, and they come back together as a liquid. So guys, the liquid water has less energy than the steam. Let's take that idea over here. So guys, imagine that we have, let's say that we have liquid water. So guys, this is liquid water, but or should we go the other way? Because this is going to be a weird conversation because it's negative. So guys, let's do this. Which number is how should we do this with the negative? So guys, let's think about it this way. We make liquid water. Now let's make steam. So guys, we make steam, and this is the amount of energy. There it is. Okay. So guys, we make steam. So we've got the steam, and as this forms, the hydrogen and oxygen had to lose 240 kilojoules to make steam. But then guys, what if we want to turn the steam into liquid water? What do we have to do? Lose more energy, right? Just like with the glass, if we've got steam with some amount of energy, and if we want to turn it into liquid water, we've got to lose more energy. That's what this represents. We've got to lose another 44 joules of energy per mole to get the steam to turn into a liquid. Does that make sense? Guys, that's what's happening on your windows. If you collect 18 grams of water, which is a mole, you know that your window has absorbed 44 kilojoules of energy, because that's the energy lost as the vapor turns into steam. So guys, the bottom line is this. The energy changes, these delta H's of formation depend on phase. So you've got to be careful of phase. Liquids and gases and solids have different heats of formation because of the intermolecular forces and all the bonding that are in the different phases. So you've got to watch out for phase when you do these. So that was a great observation. Guys, what else catches your eye? Yeah. Say that again. Isn't that interesting? Because all of the strong acids are gases before we dissolve them in water and protonate them. Yeah, so this isn't these molecules in water in their acidic form. It's actually in their gas form before they dissolve. Yeah, that's a great observation, Claire. Guys, what else? What else do you see? Yeah. Yeah. So guys, let's talk about that. The vast majority of these are negative. Guys, I would propose to you that the disturbing observation is that any of these are positive. Because guys, let's talk. Bond formation or bond breaking? Which one gives off energy? Bond formation gives off energy. And guys, aren't all of these synthesis reactions where elements are bonding together into compounds? And if they're all synthesis reactions, shouldn't all of these be negative because energy is coming out as the bonds form? They should be. But guys, why are all of them not negative? Chapter 19, we'll talk later. Yeah. Exactly. But it's carbon bonded together in a very repeated pattern. And this is, we're not going to get into it. You guys have already done chapter 19, right? I'm going to say this and then we're going to stop. So how is it that some of these delta H values can be positive? it's all about disorder, entropy. Diamond, by definition, is a substance that we know of that has very, very low disorder, very low entropy. It is so repeatable and so structured that it has very, very low entropy, which plays into the question and why its delta H is closing in on 0. But we can't talk about it until chapter 19. So guys, we've got to couch this for right now. But the question is, how can delta H's be positive? And the answer is, there's something else going on. It's all about disorder, and we'll talk starting next week. You guys good? Okay. So guys, the last thing then we need to say is this, and then we're going to do some math, and then we're going to wrap up our day. So let's get rid of this. Oh, I need to get rid of this, and then go here. All right, and so then finally this, and this you want to write down. Guys, on our list of compounds, you will notice that none of the diatomics were there. I2, Br2, Cl2, O2, N2, none of them were there. H2. Guys, the diatomic forms of these elements are understood to be their elemental forms, and therefore they don't have delta H's. All right. So y'all ready? Are you scared? A little nervous? Would you describe it as pensive? Look it up. Look it up. All right, so guys, here then is what we're going to do. Write this down with me. Actually, you know what? Don't. Don't write this down. Just trust me. So guys, now we are going to solve another Hess's law problem. What kind of problem is this? How do you know it's a manipulation problem? They gave you a subject reaction, and they gave you reactions to manipulate. You're going, wait a minute. Didn't we already do manipulation? Yeah, but we're going to do it again. So guys, I'm going to grab a sharper pen. We'll go blue this time, and something sharper. And guys, this is our subject reaction. Calcium chloride reacting with, hydrochloric acid reacting with calcium hydroxide to make calcium chloride in water. So let's manipulate. So guys, as we look at this, the molecule that really stands out is HCl. Here we have HCl. So let's manipulate. Do we need to flip this over? HCl's on the left, HCl's on the right. Again, you're not doing this with me, but guys, we've got to flip this over. HCl yields 1/2 H2 plus 1/2. So, guys, my bad. Plus 1/2 Cl2. Okay, now are we where we need to be? What else do we have to do? Double it. So we've got a 2, and we've got a 1, and we've got a 1. And then, guys, in a minute, I'll give you the delta H values, and we should double those as well. Okay? Now let's keep going. Does this equation need manipulation? What has to happen? Has to be flipped. So, guys, we've got CaOH2 yields Ca plus O2 plus H2. And you'll notice, guys, the OH is not represented together because it's from its elements. Then, guys, this. Looking at this guy, does that need any manipulation? So Cl2 is on the right, Cl2 is on the right. We've got the right number of things. We're good to go. What about this guy? Does it need flipped? No. What does it need? Doubled. So we're going to go 2, and we're going to go 1, and we're going to go 2, and now we're all good. Does that make sense? Okay, now guys, let's demonstrate that all of this adds up. So we've got 1/2 H2. No, we don't. Sorry, we flipped that one over. And guys, my fault. We should get in the habit of this practice. Cross these out when you flip them. So guys, we've got 2HCl plus a CaOH2 and a Ca and a Cl2 and 2H2 and 1 O2. Holy smokes, right? Did I do that right? I did. I may run out of space. Let's see how I do. So then we've got an H2 and a Cl2 and a Ca and an O2 and an H2 and a CaCl2 and 2 waters. And guys, sorry that got so small. So now let's start canceling stuff out. So what goes? The HCl stays. The CaOH2 is not on both sides. Is this plus Ca?
Yeah.
Okay, so Ca on both sides. Yep. Those go. Cl2s. Sorry, I'm in your way. The Cl2s go. What about the H2s? Is there, oh, so yeah. So there's 2 here, but there's 2 here. And then what about O2s? Those go as well. And guys, look at what we're left with. 2HCl plus CaOH2 yields CaCl2 and H2O. So it adds up, right? Okay. So you're like, wait, why did we just do this by manipulation if we're trying to learn something different? Well, guys, the answer is this. And some of you mentioned this, but I skipped over your idea. So now let's talk. Guys, in order to manipulate these equations, let's talk about this first. What kind, and let me erase these so you can see underneath. Guys, what kind of reactions are all of these? They're all synthesis reactions. But more specifically, these are the synthesis reactions that represent the formation of compounds from their component elements. Huh? But now, guys, notice this. Well, actually, so what that means then is we can get the delta H's for all of these things, right? Where do we get them? Right here. Watch this. Don't look at your book. Look at this. Guys, this is where this gets interesting. Look at the manipulation that we did. What manipulation? Guys, what manipulation did we do right here? What did both of these have happen to them as part of the manipulation? They flipped over. Guys, why? And the answer is not because it made them line up. Guys, what is the logic that made us flip these over? Well, guys, find it. HCl is a reactant. CaOH2 is a reactant. And guys, in reactions, reactants are not produced, they are consumed. Let that sink in. Guys, in reactions, reactants are not produced, they are consumed. So instead of needing the synthesis reactions that make the reactants, we need the decomposition reactions that break apart the reactants. Does that make sense? Now, guys, watch this. This reaction right here, did we have to multiply it by anything? No. This reaction right here, did we need to multiply it by anything? We did, and we multiplied it by this 2. Now, guys, watch this. These 2 down here, why didn't we need to flip them? Because these represent the products. Guys, CaCl2 and H2O are the products. And products are synthesized, and so those are already written correctly. Huh? But then what did we multiply by? Well, guys, we multiplied by 2, and that 2 came from right here. So now, guys, you ready to have your minds blown? Here's the summary. if we have the formation reactions for all the reactants and products in a reaction, here's what we need to do. We need to take the formation reactants for the reactants and we need to flip them. Because we don't need the product, we don't need production, we need decomposition. So we flip them around and then we multiply by the coefficients. And then guys, for the products, we don't need to flip them over, we just need to multiply by the coefficients. Does that make sense? Guys, don't look away. Guys, everything that we just said is represented in this equation. Write this down. Everything that we just said is represented in this equation. Let me remind you what we said. We said flip the reactants. We said leave the products alone. And we said multiply by coefficients. Guys, all of that is represented in this equation. Have you ever heard it taught this way? Who did that? In high school or college? Really? You had a good teacher. Guys, check this out. First of all, this. Where does it say multiply by coefficients? Guys, those are these n's. The n's are the numbers of moles, which are the coefficients. Then, guys, where does it say flip the reactants over? Where does it say that in here? The answer is the minus sign. Guys, when you flip the reactants over, we have to switch the sign of the delta H values. So subtracting these is mathematically the same as flipping the equations over. And then, guys, where does Hess's law come into this? That's good. That's the sums. So we add up the heats of formation for the products, and then we add up the negative of the heats of formation for the reactants, because those are flipped over and therefore the opposite sign, and we add those up and we get the delta H for the reaction. So guys, we are going to bleed 5 minutes into third period, which is fine. But guys, grab your equation sheets and let's talk. Find this equation on your equation sheet. Y'all see it? So it's on page 4. The third equation down. Delta H naught is equal to the sum of delta H formations of products minus the sum of the delta H, the formations of reactants. Guys, what is missing from your paper that is on the board? The N. Guys, the assumption is that you know to multiply by the coefficients. They don't give you that on the equation sheet. You just need to know it. So guys, let me show you how this works, and then we're going to call it a day. So first of all, some ground rules. And guys, it goes like this. So, let's do this together. It says, calculate the standard enthalpy change for the combustion of 1 mole of benzene to carbon dioxide and water. So guys, the first thing that we have to do is write about, I would encourage, you don't even need to write this down, just do the work with me. So guys, the first thing we need to do is write a balanced equation. So benzene is C6H6, and we are going to react this with oxygen, and we are going to make carbon dioxide, and we're going to make water. Now guys, check this out. Let's balance the equation. 6 carbons, so we need a 6. Then we have 6 hydrogens and 2 hydrogens, so we need a 3. But then, guys, we end up with an odd-even conflict because we have an odd number of hydrogens coming from here. So in order to fix that, we need to double our odd number. So this becomes a 6. But that then gives us 12 hydrogens. So that means we need a 2. And now we can balance the oxygens because we've got 12 plus 6 is 18. So that means we need a 9. Did I do that wrong? Yeah.
I forgot to change the carbon needs to be 12. Yeah.
Carbon.
Because you got.
Oh, shoot. Thank you. Sorry. My bad. So this needs to be a 12, which then gives us 24 plus 6 is 30. Okay. So this should be 15, right? Okay. So guys, this should then be 15. But this is not okay. The reason that it's not okay is it says 1 mole of benzene and we balanced it with 2. So what we have to do is divide everything by 2. And so 12 divided by 2 is 6. 6 divided by 2, 6 divided by 2 is 3. 2 divided by 2 is 1. And then 15 divided by 2 is 15 halves. See you. I'll have stuff for you next time. So now, guys, we have a balanced equation. Now we are going to solve this using our equation. So, guys, we haven't really used an equation yet in this class. These are the rules. Do it with me. The first thing we've got to do is write down the equation. So we go delta H naught. Do they include the F? No. Delta H naught is equal to sigma delta H naught formation of products minus sigma delta H formation reactants. Like so. Now, guys, the next step is you have to set this up for this particular problem. So we're going to go all the way to the left. Delta H is equal to the sum of the heat of formation. So that would be the heat of formation naught of CO2 times 6 plus 3 times the heat of formation of water minus the sum of the heats of formations of the reactants. So that would be heat of, doesn't go up there. That would be the heat of formation of the benzene times 1 plus 15 halves the heat of formation of O2. Yes, you have to do that step. Now, guys, we need, are you okay? One sec. You get the sense this just got real? Guys, if I may, as you're sort of catching up, take your time, write big, write legibly, and don't try to cut corners. Can we keep going? Now we need numbers. So guys, now we're going to go equals the sum of 6 times the heat of formation of carbon dioxide negative 393.5, I'm getting them out of the book. Negative 393.5 kilojoules. You got to put units on it, plus 3 times the heat of formation of water. But now, guys, we're stuck. Why are we stuck? We don't know the phase. We don't know if it's a liquid or a gas. On the test, they will tell you. Guys, but from experience, this gets really hot, so let's assume it's a vapor. So the heat of formation for that is negative 241.8. And that's kilojoules. And then close that minus the heat of formation of if you need to go ahead. The heat of formation of benzene, this is strange, positive 49.0 kilojoules. Then guys, check this out. Hey, Kais. How are you, buddy? I'll be with you in a minute. Good to see you. And then guys, plus 0. Right? The heats of formation of the elements, including the diatomics, is 0. So this goes away. Then guys, is it wildly unsatisfying if we don't get the answer? All right, then let's do it. So we've got, and if you guys are wondering why I use an RPN calculator, this is why. It makes it so easy. So guys, you do the math, and I'll do the math. So I'm done. That's why RPN is awesome. Is anybody else done? What'd you get? Me too. So negative 35.4 kilojoules per mole of benzene. Almost. No, that's negative. So it's negative.
Wait, so the fact that the CH6 is a positive reaction makes it even really super.
That's brilliant. Yes. Yeah. So the dissociation of the benzene is actually a net energy loser. Well, yes, and so it adds to the, weird, right? It adds to the heat being released. That's a really neat observation because it's actually an energy gainer. That energy, yeah, and so it makes it hotter. Weird, right? So guys, good? All right. So let's do this. Here then, and you've already seen this, but let's talk. Guys, this then lands you at your homework. You've already seen this. And you've already, I think, summarized chapter 19, but no, you didn't, because I said it didn't have to be due now. We need them on Thursday. So guys, our homework then is to complete this and then to complete your chapter 19 summaries. Let's take a break. We'll see you back in a few minutes. Maybe let's be back by 10:45, and we're gonna jump into lab. So go get them.